In this chapter, we're going to be looking at energy storage. To start off with, we're going to talk about a type of reaction called a redox reaction. Most energy storage is done with batteries, and batteries are based upon redox reactions. Okay? So redox is shorthand for oxidation reduction. So oxidation is we are losing electrons, reductions, we're gaining electrons. Now, when we oxidize, we say we're also increasing the oxidation number. Reduction, we're saying we're decreasing the oxidation number. Okay, so we lose electrons, we go up in oxidation number. Let's think about this for a second. Electrons, we abbreviate with this symbol right here, an E with a minus. Okay, the charge on an electron is -1. So if I get rid of electrons, I'm getting more positive. Okay, so we get more positive. Okay, reduction, we're gaining electrons, so we're adding in more negative charges. So we decrease the oxidation number because we add negative charges, so we get more negative. Okay, so our redox, we're going to lose electrons or we're going to gain electrons. Okay, and so we're transferring electrons from one species to the other. So in this little picture, X is transferring electrons to Y. So X loses electrons, is therefore oxidized and gets more positive. Y gains electrons, is therefore reduced and gets more negative. Okay, so I can take a reaction like this. So I've got this zinc and this hydrogen here. Okay, this is a single replacement type of reaction. Okay, all right, so now I can split this into what we call half reactions. So when you have redox, you have to have both processes. You can't have a gain of electrons without a loss of electrons. You can't have a loss of electrons without a gain of electrons, because the electrons have to come from somewhere and then they have to go somewhere. So zinc is one species, hydrogen is the other. So I can put together what we call half reactions. So there's my zinc half reaction. And there's my hydrogen half reaction. Now, when we balance our species to make sure that I'm not creating anything out of nowhere and I'm not disappearing anything. Well, when we have redox, because we can't create out of nowhere and we can't just disappear into nowhere, we also have to balance the charge, okay? So I'm going to assign what are called oxidation numbers to these guys. When something's in its natural elemental state, its oxidation number is 0. So my solid zinc gets an oxidation number of 0. My hydrogen gas, each hydrogen there has an oxidation number of 0. When something is a monatomic ion, its oxidation number equals the ion charge. So here I have a zinc ion with a +2 charge. So its oxidation number is also +2. Okay? Now my hydrogen ion, it's a hydrogen with a +1 charge. So the oxidation number here is +1. Okay? Now I have to balance the charge on each side of the equation. At this stage of the game, the only thing I have available to me are those negative electrons. So right now, here I have 0 charges, and here I have +2 charges. Well, 0 does not equal +2. So we got to add electrons somewhere. Well, if I add electrons over here, let's see here. This is going to give me a -2. Well, +2 plus -2 gives me 0. So my charge is balanced there. Okay? Over on my hydrogen half reaction, I have 2 + 1 hydrogens. So 2 times +1 gives me an overall +2. And then I have my neutral elemental hydrogen at an oxidation number of 0. So again, the only thing I can mess with at this stage are electrons. They're negative. So now I can add electrons over here. and I get that -2. -2 plus +2 gives me 0. Okay? Now, real important, when I look at this up here, okay, no electrons show up, correct? Well, that's because it's a net movement of electrons. The electrons come off one species and are uptaken by the other species. So when you put the whole thing together, the electrons cancel out. And when I look here, I have 2 electrons. I have 2 electrons. One's on the reactant side, one's on the product side. So if I have 2 electrons here and 2 electrons on the other side, they do cancel out, and I'm left with my target equation. Okay, so when we have redox, we have to have electrons on either side of the equation. All right, so now, how do we figure out which one's oxidized and which one's reduced? Well, again, oxidation is loss. Okay, so I have this mnemonic oil rig. Okay, oxidation is loss, and reduction is gain. And we're looking at of electrons. Okay, so let's think about this logically. Zinc got more positive from 0 to +2, and the electrons are a product. So zinc was oxidized. Okay, hydrogen went from +1 to 0, so it got more negative. And my electrons are on the reactant side, so hydrogen was reduced. When you have half reactions, for an oxidation, your electrons are going to be products, and for reductions, your electrons are going to be reactants. Okay? So taking those principles, okay, we've got our oxidation, losing electrons, okay, increasing oxidation number, reduction, gaining electrons, decreasing oxidation number, okay? So it makes logical sense with which species did what here. All right, so now, here's a couple examples. All I'm going to ask you to do here is to classify each one as an oxidation or a reduction. So in my first one, aluminum goes from a 0 oxidation state to a +3, and we have electrons as a product. So is this an oxidation or a reduction? It's an oxidation. Okay? Here, hydrogen went from a +1 to a 0, and my electrons are a reactant. So is this an oxidation or a reduction? It's a reduction. Okay? All right, take a look at these two and see if you can figure them out. Okay, well, hopefully you figured out that this is an oxidation and that's a reduction. All right, so that's the principle behind redox.